In this video, I'm going to talk about how AI is already changing the field of mathematics and science as a whole, how we do research. So this is based on the lectures that I've been giving live and also based on my marathon with Erdos Problems. So altogether, I solved over 16 Erdos problems, or I claimed over 16 Erdos problems. Some of them were already verified. That was basically coming from my prompting with GPT 5.5, 5.4, and 5.2 before that. I'm going to describe that. I'm going to describe my methodology, how I did that, and what it means for mathematics in general. Also, I'm going to give you an overview of what people like Terence Tao or Tim Gowers, Fields medalists think about what's coming next for mathematics. So this is the short lecture notes on that. So I'm going to start with what I did and basically how it's going to, generally speaking, change the field of mathematics and science in general, because it shows you what's possible when it comes to applying large language models to mathematics. So basically, Erdos Problems, Paul Erdos, Hungarian mathematician, one of the most, if not the most prolific mathematician ever. He authored over 1,500 papers and left over 1,200 open problems, of which basically half of them are solved. Over 600 right now are still open. And in this marathon that I did through April 2026, I basically attempted all of them. So what I did first was I had a codex set up to go over all the problems, generate the attempts, and then I was attempting them one by one in ChatGPT interface, prompting, and also using my knowledge, because I have to disclose, of course, that I have a PhD in mathematics and I was working in number theory. A little bit different than what Erdos problems are concerned with, mostly on the algebraic geometry side, but still those kind of problems and this kind of knowledge is, of course, very helpful when you're assessing whether, for example, a large language model is going in the right direction, and it helped me cut off some of the branches and go after the others. So Erdos problems are pretty nice when it comes to benchmarking. You probably heard by now of the OpenAI claim, of the disproof of one of the most famous ones, unit distance, problem number 90, if I remember correctly, on the great website by Thomas Bloom. But Erdos problems are really great because they have a diversity of subjects, mostly what were interesting to Erdos at the time. So those are problems like from the 50 or 60, the newest ones are probably like 20 years old, and mostly are from number theory, graph theory, a little bit of geometry and set theory. There's no newer like algebraic geometry ones or what people are considering in vogue in mathematics right now. So some of these problems were forgotten for years because no mathematicians really cared about them. So there's definitely an attention problem. That for some of these problems, they weren't like they weren't open because they were super difficult. They were open because no one cared enough to like consider spending I don't know, a week, a month trying to solve one of them. This of course changed with AI, and this is why I think it's very interesting, because AI is really good at approaching stochastically a lot of problems. If you especially have a list, like a list of Erdos problems, and in this website by Thomas Bloom, erdosproblems.com really help, then this really helps you understand what's going on. I might show you the website to show you what really it looks like. You have the problem here. For example, we go after a problem 90. This was the unit distance problem that I've mentioned. You can read the comments people post here and discussing, for example, various constants or maybe different approaches to what can be done. This is really cool stuff, and this also makes for why the problems became famous as a benchmark, because there's a whole community, and there are people like Terence Tao commenting and other known mathematicians on it, together with OpenAI, DeepMind, and other companies trying to they hand at the problem, because you have a lot of attention right now. So especially except for me, apart from me, there were other entities that actually did all of the problems. So for example, DeepMind attempted all of them. They had a couple of papers, for example, Alpha Proof. They solved actually less problems than I did in the end. They have better methods, of course, because they have like the whole harnesses that they can use for other problems. I did it very specifically for Erdos Problems, but in the end I solved like over 16. They did, I think, like 12 or 13, DeepMind team. OpenAI probably solves pretty much similarly, but they solve much harder problems also. Like problem number 90 is, of course, much harder than anything that I have attempted or tried to solve here. Of course, I did try to solve it, but basically after getting one prompt or maybe two prompts in, I knew the problem is super hard, so I just skipped that. This is generally the strategy that I did for all of the problems. If there was like nothing interesting after 1-2 prompts, and I deemed that there's like no easy way out or maybe nothing manageable, I just skip the problem and go to the next one. This is very different to what usually human mathematicians do, because they obsess about one single problem and they try different ways, they come back to the problem. Here it's a little bit different. The full list, 600 problems, and then you try to pick and choose the problems that seem to crack, are really ripe for doing something because maybe someone forgotten about them. And this is a good example of one of those problems. So this is one of the first problems that I solved with GPT. Commented nicely by very nice by Terence Tao. This problem actually used one of the results by Tao and Teravainen, and basically the solution was like 3 pages long in the end. Most of the work was one small lemma, pretty standard one in analytic number theory on the irrationality, and the other one is using this result of Tao and Teravainen from the last year, from 2025. So it shows you that those kind of results, some of them became possible to solve cleanly and fastly just recently, because there was like theory building around the subject. And so this is all of the claims, all of the problems. You can verify them on the website if you go directly on Erdos Problems. I posted all of the solutions here so that like others could comment on that, so nothing is hidden really. You can see everything online with people commenting on that as well, because I think that's the best way. Of course, none of them are verified in the sense that in normal mathematics, when you have a claim for the solution, you write the paper, you send that paper to a journal, and then you wait like a couple of months, maybe a year, maybe 2 years if it's super difficult for the review, and then it's considered to be verified. It's a little bit different right now, and this is how already mathematics is changing. Because right now with mathematics, I could generate plausible papers in hundreds, if not in thousands, on new results, and basically could spam, all the journals with new entries. And this is happening to some reason. I'm not doing that, of course, but there are a lot of uptake in how people are sending a lot of papers to different journals. So something must change. And one of the things that is changing here is auto-formalization, on formalization in general. So there was this idea already like a decade ago about, or even it's actually even older, when computers came around, that maybe some of the arguments, some of the proofs could be formally verified. It means that it could be translated from ordinary English, however mathematicians write the paper, to a language that is checkable by a machine, a little bit like a compiler does with the code. So you basically run it through the program, and if it says it compiles, then means the proof is correct. One of those languages is Lean, but of course there are many others like Hall, Isabelle, Mizar, and a bunch of others. And basically the whole idea is that you would put those proofs into that, and then you would know that the proof is correct. And in this example that I'm showing you here, also Erdos Problems forum cares a lot about whether the proof is formalized or not, mostly in Lean. This is where most of the formalization goes because of the mathlib library, meaning there's a whole library of sets where you can build from, of different concepts, and it makes everything much faster, especially that there's a tool, Aristotle from Harmonic, which is available for free for auto-formalization, which is really good at doing that work as well. Formalization is not free in general, meaning it takes time, it takes resources. It's not possible for every domain of mathematics. It works here very well because those problems are more on the elementary end. But for example, it wouldn't work in algebraic number theory, arithmetic geometry, or a couple of other domains where you have to really have a lot of different concepts formalized first as even definitions, because definitions are the hardest. So what I wanted to mean here is some of the proof that some of the solutions that I claimed came instead with this lean formalization. So I formalized them in lean so that I knew that the proofs are correct, and then I could submit both the paper written for mathematicians for like in a standard tag and both the lean file to verify against. And it's making the whole work much faster right now. So you can really do it much faster than if you were to do it before, because you don't have to formalize by hand. You can formalize using these tools, and it makes the entire process much faster. But still, human digestion is one of the main problems. So even if you submit the proof, it doesn't mean that other mathematicians will read it. And this is one of the problems that I'm going to tell you in a moment about. So generally speaking, this AI plus human in the loop, in this case that was me, really could cover a lot of those problems from different domains. It wasn't just pure number theory, like primes, irrationality, and so on. We also attacked problems in graph theory, set theory, geometry, and distances, analysis with a couple of like complex variables questions, which is really interesting. And generally speaking, it's really good at finding this 1-2 tricks in particular problems that are missing. So for example, if you have a question and generally there's like a 10 pages long proof, up to 10 pages is generally speaking my safe zone. If the proof is around 10 pages or less, it means most of the time that the proof is correct. For GPT-5.5 Pro, this is the model that I think I have the most faith in. Above 10 pages, it gets tricky. Those models use coherence quickly. They use they lose context. They make errors. Even if you try to correct these errors, that keeps coming back. So you have to keep that in mind. For now, 10 pages or 12 pages is probably the maximum you can expect without major errors. And of course, it doesn't mean that they get everything right all the time. So you have to accept that probably like 95% of the time, 10 pages will be fine. But again, this is where I'm coming in, reading the papers, trying to see whether the arguments are correct, double checking everything, doing everything a couple of times, because the workflow is basically, I have the problem list. I'm doing this agentic approach, trying all of the problems first, very quickly generating the attempts, what might work, and then start prompting them myself, crafting the right prompts for the problems that I think are solvable or are maybe easier, and then going one by one. So the first stage, agentic, is going through codex in a terminal, then looking at everything that I got, and then going through ChatGPT interface and going one by one through every problem, and then going back and forth. Usually I'm not doing more than 4 prompts, which I already mentioned. I'm going to talk about that in a moment as well. So agentic approaches make sense here because you can pull exact statements, you can collect references, do some small computations, and then you already have a good package to start with, attempting those problems much deeper. Again, this makes sense if you have a list of problems. Of course, you can do that for any single problem, but especially in this way, you quickly see what problems are easier to crack than the others. Now, prompting LLMs for research mathematics. You usually should come with the methods that are probable to solve the problem. That's usually easier. Of course, that's not always the case, but sometimes we know that. Sometimes we know that maybe this kind of method would work. Ideally, because if you try to see, like, just give a statement to the LLM, to like GPT, and say solve this problem, then usually what happens, especially if it's open problem that's open in the public, it won't even attempt the problem. It just gives you some kind of excuse or maybe references, and that's it. But usually that can be overcome. You can just say, hey, try this method on this problem, or maybe if you don't know the methods first, you maybe have a look at the literature and tell to the LLM, actually generate me different approaches that might work, and then try to get into those. This is usually how I worked when I didn't have an idea for a reference, for a method. And basically this overcame this this fear of attempting open problems. Also, in the end, it's super important to try to break the proof, meaning doing double checking, finding the errors, being the critic. If you just open an additional window in ChatGPT or Claude and ask, giving the paper, giving the notes that you already have, find the gaps and errors. Usually it will find them. And I think this is a good thing to do as a first step. It doesn't mean, of course, that the proof is correct yet. To make sure of that, you need to formalize it properly, or ask human research mathematicians do a proper peer review to do it. But usually running this kind of adversary is already a good first step. So my 4-prompt heuristic is basically that over 4 prompts, there's a risk of coming into the loop, and basically you keep on repeating the same errors and nothing really works. And if I won't find something useful in like up to 4 prompts, then basically I skip the problem and go after the next one, unless I really like the problem, or unless I think like there's a great method to try it, and I try to, but then still I mostly clear the conversation, start from scratch, and then just give a different prompt about the same problem. I don't think like going after 4 prompts makes usually sense, because this is, again, the models lose their the kind of the context, coherence. They keep on making the same errors. So this is what worked the best for me. Again, this is a particular artifact for GPT-5.5 Pro, Claude, and the current generation of LLMs. This might not be true for the future models, and basically with what I'm trying to do at Ulam AI and producing the interesting data, I'm exactly trying to solve this kind of problem, because in the end you want to have a model that's able to hold the conversation for much longer and do interesting stuff. Now we're coming back to what's really interesting, and those recent talks by Terence Tao at Future of Mathematics Symposium, which I really recommend. The videos are on YouTube, and he was talking about how mathematics is changing and what's really becoming crucial in this world of proof abundance. We didn't have this word before because proofs were difficult. Producing papers with proofs was difficult. That's not the case anymore. The problem right now is, of course, LLMs won't solve every problem. They especially won't solve like super hard Riemann hypothesis type of problems. That's still a long way to go. They can solve, however, already interesting problems that would make great PhD theses. And looking at the progress in AI, we could expect that they will solve more and more problems like that. So what's going to happen from the pure mathematics perspective is that you probably should focus more on trying to understand what's happening. And the role of the humans is shifting a little bit towards not who's going to prove that first, but who's going to explain that better, who's going to explain it the best. And generally speaking, this human digestion is a very important part in the end. Community review, and generally the measure of success is whether we can do what enables people to think and understand more clearly. This is the words of Terence Tao. So this is the kind of the data that I'm getting from working with these models. Basically, those are like, if this is just a short word for people more interested in AI side, this is great for different reinforcement learning with verifiable rewards systems. You can nicely extract different data coming from this human AI conversations that then will be a basis for the next generation of models, because you can have this proof verification units with like it's a little bit different than just going with a very simple problems of where there's a final answer and you know that answer, because here with open problems you don't know the final answer. Usually you have some steps in the proofs, but you can already reward the model by coming with those partial results. So I think this is pretty cool, and this is something we have to work with if we want to progress AI in general. Again, we're coming into the zone from proof generation to proof digestion. The most important stuff is the statement exactly right? Where does the proof rely on known theorems? Which lemmas are genuinely new? Can it survive formalization or public scrutiny? So this is coming from Tao. He also commented that on Erdos forum. In an age of proof abundance, quality and digestion matter more than dumping food on the table. table. You really care about how great different arguments are explained rather than whether something can be proved very fast. Of course, the proof is still important. I think this is like a very nice thing to do it, but I think this incentives for where interesting science lies will be changing with LLMs, because it has to change, because right now anyone can produce proofs much faster. It's of course not at the professor level yet, but it's definitely PhD level very fast if you can ask the right questions. This is also coming from Tim Gowers, another Fields medalist. He wrote about that on his blog post, in a blog post on his blog, about that the problem that he was looking at, and basically got a PhD level research in an hour or so with no serious mathematical input from himself. He just prompted ChatGPT Pro 5.5 Pro to get the result. And you get very quickly a publishable looking contribution, because you get the paper, the models write the paper, and you can, in principle, you could already submit that to a journal. Of course, if you can do that in 1 hour, just imagine, and there are like, thousands, millions of people doing that, then the entire system really has to change, because we can't really accommodate this many proofs, this many papers coming into the system, because again, the bottleneck is human attention and human peer review process. So we really have to change that. And this is where we keep coming to the same question. Formalization is really part of the process, and probably this will be even more and more important along the way. When I was starting and doing my PhD in mathematics, I heard about formalization, didn't find it really interesting. This was like super niche, small domain. No one really cared about that outside of people, maybe in, like on the verge of computer science and mathematics. That was like a pretty sub niche that people were doing for the sake of maybe having like a formal way to do stuff. But most of mathematicians didn't care about that, and that vastly changed right now, because this really will make the work of mathematicians and scientists in general much faster. The promise of Lean and other languages is that you'll be able to formalize arguments, scientific arguments, so that not only goes for mathematics, but also for physics and other STEM sciences. So I think this is pretty interesting, and this is where we're coming to right now. LLMs will get better, human attention will not get vastly, we won't get much more of the human attention, maybe less even so. So we need other systems for peer review or reviewing mathematical works and other science, because the goal should be, we want to progress with science, so we want to make as many proofs as possible, as many of interesting problems. We want to solve them, write more papers. There should be other systems than arXiv. There should be other ways to verify the papers, the work, and so on. So it's all about the question of infrastructure. It's going to change. We don't know yet how. This is something that I'm super interested in, like the alternative system to arXiv, to publishing, to some extent automated in a way such that with this new abundance of proofs, we're still able to find interesting information from human perspective and be able to organize and comment around that. I think Erdos Problems work amazingly well for that. This is like a blueprint for what's possible when you have a forum where people who are not working academic mathematicians. I used to be one. I'm not really affiliated with any university right now, but even amateurs that do not have a PhD in mathematics are coming to the forum and can really give you some kind of input of what they're doing, using LLMs and doing useful work as well. So I think this is amazing, because you can have on one forum this kind of people, and in the end, those people produce papers and solve the problems. Something like that might be an interesting input towards what we're doing here generally with mathematics. Of course, full mathematics is a little bit harder. You have arXiv, you probably would have to have kind of a social layer to arXiv and maybe something else, but basically allow people to discuss, allow LLMs to have an input as well, and then a discussion around that should be organized so that it's easy to find what's happening. What to expect next? So there's a great essay by Kontorovich. He wrote about how the formalization is basically becoming cheaper and cheaper, and the work is going faster. For comparison, there's, for example, this famous work on Kepler's conjectures that took really over a decade to formalize. With the current methods, that probably would be less than a year if it were to be, maybe even faster. So it's not yet super fast. Formalization also is not an automatic tool. You have to remember that you still have to care about, for example, whether definitions are right or whether you really formalized what you were trying to prove. So this is a little bit of a different problem, and it still is a problem. It's not like if you formalize something, if you get a lean produced by LLMs that it compiles, then it doesn't mean automatically that you have the right proof. You still have to make sure that the lean corresponds to what you have and that you're proving really what you wanted to prove. So this is another kind of problem. But the cost of formalizing are really going down, and it's really nice for the for what we're coming next. So this is also where my move 37. So if you remember in AlphaGo, that was like this famous move that basically changed people's conception of what's possible with the machines. My move 37 in mathematics would actually be new definition, not a proof. And this is the same goes for formalization and informal mathematics. Definitions are hard. Formalizing some of the definitions, especially like Shimura varieties, étale cohomology, or even Hilbert modular form, so my domain, this is not done, and this is very hard. And this is very hard for a reason, because there are different layers of abstractions. Erdos problems do not have layers of abstraction. There's a single layer. The problem that you can most of you can understand, even if you don't have any kind of background in mathematics. But for example, with things like Shimura variety, if you don't have background in algebraic number theory, algebraic geometry, or and a lot of number theory, you won't be able to understand that. And not only that, you probably will spend months trying to get really to what the definition is saying. Same goes for étale cohomology. Same goes maybe for, well, Hilbert modular forms are a little bit easier. But if you want to study things like absolute Galois group action on étale cohomology of various Shimura varieties, then you have so many different layers of abstraction, then basically you can't really formalize that currently. You can't really reason with in a formal way about it. And also from the purely definition perspective, LLMs would not come with a definition of Shimura variety. This is the kind of things that I'm getting at. This is the kind of experiment that is still to be seen whether it's possible, meaning that you basically would like them to come up with a new theory, making a new definition that is so striking that basically gives you new tools to approach new problems. For example, this was the case, for example, with perfectoid spaces by Peter Scholze. This allowed to open new ways in mathematics, and this would be basically my move 37 in mathematics. This wouldn't even be, so I don't really care about the new proofs. I believe that they will keep happening, and of course this is super impressive, but the most impressive stuff that I would be in mathematics from my perspective, and probably from other mathematicians as well, is that you would have a new concept in mathematics that would open up new fields. This would be amazing. And of course, this would be basically fields level work, super intelligence coming. Basically, AGI is here. This is like new definition on the level of perfectoid spaces. Basically, AGI is here from my perspective. Now, from the credible AI mathematics, again, this is the kind of the questions that are coming back. And as I've mentioned, really, what's really important is not only provenance, who's doing the proof, what kind of LLMs have you used, but also digestion, verification, and data used along the way. I think we're living in very interesting times for mathematics and for science in general. We're going to see amazing proofs coming along the way. We're going to see definitely a lot of things breaking down in academia, because the process right now in academia is that you keep on publishing, you keep on getting results, and then you apply for grants and you get incentives this way. But what happens when your publications are actually, already some kind of a work, you want to apply with your publication, but it happens that already some kind of LLM had this kind of work on the GitHub, because someone ran an LLM, generated 1,000 proofs, and one of the problems that your PhD thesis was on is actually already on archive. So we're coming into this area of plagiarism and whether that counts and what to do about it. And I think those are not easy questions. And that's why the entire field has to change a little bit. And of course, another question is how mathematicians will use LLMs themselves. A lot of them are already experimenting with that. I think it's definitely early right now. Not all of them heard about the revolution coming along the way, because this is a pretty new stuff. Basically, all of that happened since December 2025, and the pivotal moment was really the release of GPT 5.2, which was the first thinking model, the first reasoning model that was able to generate interesting mathematics and be useful on open problems like Erdos problems. That was December 2025 was the moment when first Erdos problems were solved with GPT, with AI in general. And from then, it's only getting more interesting. So we're going to definitely see a lot of progress because those LLMs are getting better. So we're going to see very interesting stuff coming along the way. Thank you for watching. Let me know in the comments if you have any questions. Generally at Ulam AI, I'm working on different math benchmarks, evaluations, data, testing models on various open problems. So doing both mathematics and AI stuff. And on this YouTube channel, I'm going to talk even more about that soon. So subscribe and see you in the next video.